Thanks, Martha, and thanks to the committee for this nice opportunity. And I'd like to update everybody on recent progress in organic photovoltaics and a couple new ideas in the field. So before we begin, I want to thank a lot of contributors to this talk. This is sort of the synthesis of a lot of discussions I've had over really the last couple years with collaborators. And in some cases, some of the people on this list have given me data that you will see. So certainly Yang Yang at UCLA, Moritz Riede, Carl Leo at Institute of Applied Physics in Dresden and associated with the company Heliotech, Kees Hummelinen, University of Groningen, Ahmad Zen from Bosch Singapore, Christoph Brabetz now at University of Erlangen Nuremberg, Changi Li, Seoul University, Andrew Hertzing and Dean de Longchamp at NIST, and a whole cast of close colleagues at NREL who have contributed to some of the information in the talk. So I'd like to start with a little historical note and maybe sort of give you a new perspective that organic photovoltaics is quite an old field, actually. So the very first report of an organic solar cell was way back in 1958, just a few years after the start of the silicon solar cell technology. Now, they weren't quite sure how to make a good device back then. This initial device was a heterojunction, but unfortunately both materials, this magnesium phthalocyanine and tetramethylphthalodiamine, they're both p-type materials. Well, it's not really a heterojunction, but nonetheless they were able to get a little bit of photocurrent and a tiny amount of power out, in this case 3 picowatts worth of power. So nonetheless, over the preceding decades, there was sporadic developments in the field. There was early work on crystalline tetracene and on phthalocyanines, and then in the early 70s on polymer systems, polyvinyl carbazole. But really in 1986 was sort of a watershed event with the 2-layer heterojunction device developed by Chin-Tang at Kodak. And this was really a true heterojunction that had a PN component. So starting the time scale in 1995, the next development was the use of fullerenes as acceptors, as a very efficient electron acceptors. And the field continued to grow as more researchers got into it, more technologies advanced, and over the last several years we've seen a little uptick in the efficiencies. So fast forward to just a few months ago, and we've had actually a quite exciting realization in the field, which is an efficiency over 10%, sort of past the 10% barrier. This was demonstrated by, of course, the very large corporation Mitsubishi. And this is a press release. It's a little bit fuzzy, a physical press release, and that actually is indicative of a little bit of our information about this device. Mitsubishi has been working in relative obscurity over the last couple years, and over the last several months have said, oh, by the way, we beat you all. We have over 10% device. So very exciting. They're also claiming module efficiencies of 6 to 7%. Now we know a little bit about the device. We know it's made from a benzoporphyrin derivative, and it's initially a soluble, chemical soluble process that is made insoluble. I'll talk a little bit more about that. So there's a whole host of companies now trying to rapidly develop organic photovoltaics. These range in size from relatively small startups like SolarPress and Oscilla, which are in the UK, to large multinational corporations like Mitsubishi and Bosch. And then some companies that are sort of between that area, Konarka, fairly mid-sized company at this point, Heliotech, Plextronics. A lot of these companies have demonstrated and certified efficiencies beyond 7%. In the case of Konarka, Heliotech, and Solimer, have efficiencies exceeding 8%. So not only are the champion devices reaching new heights, but there's a lot of breadth in the field and a number of companies working in the area. So you can purchase OPV products, and these are now really just niche consumer electronic applications. We're not talking about rooftop power quite yet. But you can buy sort of a satchel that has OPV integrated for charging your cell phone. You can get some awnings that would go over some tents. If you go to San Francisco, go to a number of the bus stations, you'll find OPV product that is above the bus station and you can plug in and power your portable products. And then finally, there are some building integrated demonstrations with a little larger area producing a semi-transparent window. So all of these products really are from Konarka Corporation. They're sort of leading the way in industrial products at the moment. And as I said, you can obtain some of those at least yourself. And other companies are working rapidly to develop these technologies as well. So it's a little hard to define what is organic photovoltaics. It's a very broad field, and there are many different types of materials. If you go to our article from 2005 MRS Bulletin, you will see sort of a panoply of different material types and architectures. One can consider hybrid polymer oxide devices as containing some organic component. One can consider the solid-state dye cell as being organic, since the dye is an organic component. But for the purpose of today's talk, I'm speaking strictly about fully organic devices, so no inorganic component that is absorbing light or doing charge transfer. And we have two broad categories for these devices. One is a solution processable device, which we normally process into a bulk heterojunction, blending the electron donor and acceptor together into the active layer. Or a thermally evaporated device, where we thermally evaporate relatively thin layers, actually very thin layers, into a multi-layer strategy. So two types of processing strategies define the two regimes of molecules. So one of the advantages of organic photovoltaics that we tout is the enormous array of molecules that we have access to. And I just give you, of course, a small sampling here, but some of the major ones. So phenylene derivatives, where much of the work in the 90s were based on thiophene derivatives, much of the work of the last decade, and still currently the leading fruit fly of the OPV world is P3HT, poly3-exylthiophene. These materials do not have very good band gaps in terms of absorbing the solar spectrum. So more recently, more sophisticated materials have been developed. And these are typically copolymers that take advantage of an intramolecular charge transfer to reduce the band gap, something closer to 1.4 electron volts. So a couple commonly used materials, PCD, TPT, PCD, TBT. I just reversed those, but you get the idea. PTB7, these are all various copolymers. And frequently you will see this benzothiodiazole moiety, benzene with this diazole. So that is a good electron acceptor that acts to reduce the band gap within the material. Beyond that, we can think about some small molecule materials. This includes the phthalocyanines, the porphyrins, and oligomers that can all be thermally evaporated. And then we have some small molecules largely based on fullerenes that act like electron acceptors. And finally, a material that we can process from solution, but is also a small molecule. So there's a number of different ways to categorize all these molecules. One way is to say the blue squares are all polymers, so we can process them from solution, spin coat films, print films. The green curves now are small molecules that we can thermally evaporate and use vacuum deposition for. And then finally, this guy is something that is a small molecule that we can also do solution processing. Now, another way to bin these is by their electron donating or electron accepting character. And largely, the electron acceptors are fullerene based. This is a bit of a problem in the field, so that we have a really wide variety of electron donors, which is everything else, and a relatively small population of electron acceptors. So again, this enormous variety of molecules is one of the great strengths of OPV. When you ask what is an OPV device, you have this infinite array of molecules to choose from. So that's very good, and it helps to write a good proposal. But it also brings along many challenges. So when you actually go to do the work, you have to ask, actually, what subset of infinity am I going to choose to make for my device? And so this is a big problem, and it's a particular problem for small university research groups that don't have in-house synthetic capabilities, and it may be difficult to obtain some of the materials. I'll speak a little bit about that again later. So the devices themselves have two different geometries. We can make what would be called a normal device, where we have a low work function metal electrode, a negative electrode, and we sandwich the active layer between that and usually an ITO-based positive electrode. So we extract charges, negative charges from the top, positive charges from the bottom. We'll call that the normal device. We can invert the structure. So if we use a high work function top electrode, which can be gold or more commonly silver that we let oxidize a little bit, then we can extract the positive charges from the top. And what we do is insert an electron transport layer like zinc oxide, or can be TiO2, on top of the ITO to invert the direction of the device. The inverted device is a lot more promising potentially for commercial applications in the sense that there's no low work function metal that is on the normal device that could potentially oxidize. So just keep in mind these two different strategies for device fabrication. So just to give you an idea of the general structure for such a device, so this is an inverted device, cross-sectional TEM, imaged by Julia Shu, who's now at Dallas. So here's our ITO, a zinc oxide, typically about 20 nanometers. The bulk heterojunction, which in this case is using zinc oxide as an electron acceptor, but as I mentioned, this is normally a fullerene. And then this positive electrode on top, which we can sometimes put in a buffer layer of P dot to help extract the holes. So I want to point out that these are really very thin devices. Active layers typically 200 nanometers. So that is enabled by the high optical extinction coefficient of organic semiconductors, which is typically over 100,000 inverse centimeters. So we really don't need much material to absorb the light. So that's a good thing, because in the balance of charge carrier mobility and carrier lifetime, we only get a carrier distance of a few hundred nanometers out of these devices. So if we tried to make this 1 micron thick, we would suffer from massive recombination. But luckily, Mother Nature is kind to us, and we get the necessary optical absorption. So in a critical quantity in the bulk heterojunction, and by bulk heterojunction I mean mixing two components together, the electron donor, which is typically the polymer, and the electron acceptor, which is typically the fullerene, the details of that mixing are critical for the charge transport and recombination. And really, it's not only been recently that we have some decent understanding as to the nature of the nanoscale mixing of those two components. And a lot of this recent work has come as a result of transmission electron microscopy. And this is an example that was provided by Dean DeLongchamp's group at NIST, and they have some of the best instruments in the world for this. So this would be an 800 nanometer field of view. And in this case, the red component, which we'll separate out pretty soon, that is the polymer component, and the green component is the fullerene. So what you see is some linear structures, some nanofibrils. That's a result of self-organized growth of the polymer. And then the remaining structure is the void space that's filled with fullerene. So there are a number of issues with this picture. First of all, we don't really know if the red plot is only polymer and the green plot is only fullerene. There's a chance that there is some intermixing of a few % of each component. So we don't have the resolution in the elemental analysis to fully understand it. Second of all, we don't fully understand what we want. What is the ideal morphology? Do we want 1% of acceptor in the donor or 1% of polymer in the acceptor? We're not completely sure about that analogy. Thirdly, the other thing we're unsure about is how to achieve a given morphology. So I showed you these molecular structures. We process those either through vacuum deposition or through solvent processing. We don't know in the beginning what this structure will look like at the end. So that structural property relation is one of the big mysteries in the field. But nonetheless, through some intuition and a lot of hard work, we can get morphologies that do have sort of nice charge transfer percolation pathways, and we can get charges out of the device. So in this TEM, we can scan up and down through the z-axis and get a good three-dimensional picture of the device. So more recently, people have tried to do what we'll call an ordered bulk heterojunction, or make some nanopillar structures. Of course, the idea is clear, to make some straight highways for the charges to move up and down to the electrodes. And actually, this has been tried for a little bit of time. Steve Forrest's group is working on this already about 10 years ago and have been publishing on it recently. Tokyo University group by Hirata and Adachi have published recently on growing nanopillars of parylene, PTCDA, with copper phthalocyanine. And so this is very important because the Mitsubishi result, the 10% result, is actually from such a structure. So what they have done is grow a porphyrin material from a solution processable molecule, make a bulk heterojunction blend of that, but then thermally anneal it to induce growth of nanopillars, both of the fullerene and of the porphyrin. So now we have intercalated nanopillars of both components, and we get something that looks like the ideal, we think, cartoon of nice charge percolation pathways. So this was published a few years ago. As I said, more recent details are a little bit fuzzy, but it's a pretty good bet that the 10% device looks a lot like that in the active layer. So what is the photophysical mechanism for operation of the devices? Well, we can do at least a little cartoon picture here. So we excite in the one of the materials, typically in the polymer, will be the stronger absorbing material. We excite an exciton, which is this bound electron hole pair. The exciton is bound by a little bit of extra energy. That's why you see this dip in the LUMO level and a little increase in the HOMO level. So that exciton should, in principle, diffuse to the interface where there's an intermediate step called a charge transfer exciton. At least we think that exists. This will exist for a few femtoseconds. And then finally, there will be real charge separation where there's an electron on the accepting material and a hole on the donating material. So importantly, this forward electron transfer process is an ultra-fast one. So it's been measured by Christoph Brabetz at something about 50 femtoseconds. But the backwards rate, the recombination rate, is extremely slow, something like 1 microsecond. So it's this asymmetry between the two rates that really enables the organic solar cell. So to give you an idea of device performance of a high efficiency but somewhat standard device, I cite Yang Yang's work from UCLA. And he had published a 7.4% device based on PTB7 and C70 derivative. And what he's done is tried different processing techniques, different solvents, and finding the ideal combination was able to get a 7.4% device. So typical numbers are current of about 14 milliamps per centimeter squared, open circuit voltage about 0.7, fill factor of 70%. So we can do a little bit of thermodynamic analysis on this system and see where the losses are. So first of all, we can look at the band gaps of the two materials. So we have this PTB7. This is the polymer, has a band gap of about 1.7. And then the C70, band gap of about 1.6. So approaching the nominal optimal of 1.4. Now importantly, the C70 is not a very good absorber. And its spectrum is given here, but it's only a relatively small portion of the spectrum relative to PTB7. So this is the total EQE. Its average is about 60% from up to about 800 nanometers. So if we take a look at the individual characteristics, again, we have a current of 14 milliamps per centimeter squared. If we use an ideal Shockley diode equation, with that band gap of 1.6, we'd expect a current of about 22 milliamps. So we're losing about 35% in the current. VOC, 0.74. The ideal case would get about 1.4. Here you see a really big loss, about a 50% loss in the voltage. Fill factor, we're losing a little bit less, 24%. But in the end, we've lost 73% over the ideal diode equation. So I want to point out that the VOC is one of the biggest losses that we have to deal with. So how do we model that photophysics in a little more detail? Well, we use a kinetic model and try to understand all of the rate constants between the different states of the device. So a relatively simple version of it is that we start with a material like the donor, which we excite to form the exciton. Then we form this charge transfer state, that intermediate charge sharing between the two materials. And then there is generation of free carriers, hopefully. Now this process can go backwards through recombination, or we can get ground state recombination that is a removal of energy from the system. So this model was published initially by Koester about 6 years ago. And by fitting a variety of parameters, we can get a pretty good estimate of what the ultimate charge generation of free carriers is out of the device. So we can incorporate that into a full device model to analyze the JV curves. So I won't bore you with the details, but these are more or less standard device equations you would find out of, for instance, Z's book on semiconductor physics. We're solving Poisson's equation, continuity equation. And we're doing this in one dimensions and just solving this numerically. So this is an ongoing project that we're doing with Peter Graf at NREL in the Scientific Computing Center. And what we can do with this in the end is fit a JV curve. So this is some data that was from NREL. It was given to us by Dana Olson and Andres Garcia. And this is about a 7% device from this material, PCD TPT. So what we have is a whole range of inputs: charge generation rates, density of states, recombination rates, mobilities, temperatures, and so on. And through careful fitting of the data to both experiment of the individual quantities and the JV curve, we can get a reasonable idea of what the device physics is. So there's more details in this, though. I mentioned there's the charge transfer state, that intermediate state. And the thinking now is that that actually drives a lot of the device physics and the generation of the voltage. So for one thing, if we look at that charge transfer state and we plot on an energy scale relative to the singlet state of the absorber or the triplet state of the acceptor, the only way we're going to get a device to work is if the charge transfer state is lower in energy than both of those. In either of the other two cases, there'll be no charge generation. So we need that CT state to be a little bit lower. Now, the exact details of how much lower and how much loss is associated with that is still a big matter of debate in the field. But at any rate, recent papers have showed that if you plot the difference between the HOMO of the donor and the LUMO of the acceptor, which should be the maximum voltage of the device, and plot that versus the charge transfer energy measured through spectroscopy, you do get a nice straight line. I'd like to bring up one little trick that was published recently by Yang Yang's group at UCLA, and I really like this. So what he has done is to intercalate a ferroelectric polymer into the device at one of the electrodes. And by electric repolling device, this induces a large built-in field into the structure. And the idea is to have a large built-in field that will break up that charge transfer exciton, that CT state, and to hopefully get more current out of the device. So one can plot the charge density in the device, and at the dielectric layer, the ferroelectric layer rather, we get a large separation of charge. And what that does is to increase the built-in field in the active layer. So what Yang's group did was to show that the fill factor of this device increases, the short circuit current increases, the VOC increases a little bit. So a nice bit of device engineering. And I like this because it uses a new material and shows us something about the photophysics as well. Okay, a little bit more about the voltage loss. And this gets into the thermodynamic part of the talk. So when we look at the relative band structure of a typical set of materials, typical is poly-3-hexylthiophene and PCBM. So we have the HOMO and the LUMO of the polymer, HOMO and LUMO of acceptor. We have this quantity, the band offset. And this is now the thermodynamic loss in the charge transfer event, delta G. In a typical device, this is an enormous quantity. This is well over 1 electron volt. So when we do that charge transfer process, we're losing all this energy to heat. What's left is the effective band gap, the difference between HOMO of donor, LUMO of acceptor. This is now the maximum voltage we can get out of the device. So the question is, how much energy do we need to lose to drive the reaction? One can expect that we need some driving force to drive the reaction. But if it's too small, then we don't induce this event. So that's really an open question in the field, is how large can that, or rather how small can the delta G be, and therefore how large can the voltage be? So there's a number of different groups looking at this through synthetic chemistry to change the band offsets. And let me just offer one perspective on this problem. So what we can do is go back to our kinetic scheme and draw a simplified version where we remove this charge transfer state business for a little bit and just consider where we have an excited state donor and an acceptor, which we can go through to create free charges, or we have a ground state where we lose energy. So if we apply the standard charge transfer theory, and that standard theory is Marcus theory, which is developed for electrochemical charge transfer reactions, but we think it's valid in this case as well, then the critical component is the reorganization energy. That is, when you move a charge from one molecule to another, what is the energetic change in the distortion of all the bonds? Right? This is a critical component in the charge transfer and how to dissociate the exciton. So what we can do is calculate efficiencies based on, first of all, delta G. I have written here delta E, but it's really delta G, the band offset. And we can, putting in a conventional value of the reorganization energy of 0.8 electron volts. So with that value, we can fit the current data, like the 7% device I showed you. We can fit it pretty well. And as you reduce delta G, you see that efficiency goes up because voltage goes up, but it'll crash at some point because the driving force becomes too small. And in this regime, we can get efficiencies something around 8% for this large delta G, and maybe up to about 12 to 14% for small delta G. However, and this is the new idea I want to bring to you, if lambda is very small, if we can make materials that have a very small distortion of the molecular bonds, this would happen if the bonds are very rigid, or if the donor and acceptor are lined up just in the right way, then we get a completely different plot. And in this case, the efficiencies now start at something like 10 for large band offset and go up actually above 20 for small band offset. So in the limit as we have small band offset and small lambda, we actually approach the Shockley-Queisser limit. Of course, this is strictly hypothetical. We're thinking about synthetic ways to do this, but it adds some promise to the field. I want to point out that my colleague Case Homeland will be giving a talk on Thursday and discussing a couple different ways that one could think of very high efficiency OPV, above 20%. We have a couple different schemes that could potentially get there, at least hypothetically. Okay. So beyond the single junction, of course, we want to work on tandem devices. And a tandem device for organic photovoltaics is a complete no-brainer. We have the advantage of easy processing of the materials. We can solution deposit. We can vacuum deposit. There's an additional benefit of organic materials, which is that the absorption spectra are relatively narrow relatively narrow bandwidth. So in fact, it does not matter the order in which we put the bands. We can put the low band gap component on the bottom or on the top, and it'll get absorbed. Light will get absorbed as is needed throughout the device. So this is not a new idea. Rene Janssen's group has worked on this already about 5 years ago. They're able to make something like 3 or 4 junctions stacked on top of each other, I think up to 5 actually. And I want to point out that the Heliotech 8.3% device is a tandem architecture that's been thermally deposited. I refer you to this review paper by Christoph's group on organic solar cells. And there's really a myriad of ways to fabricate these. What's really critical is, one of the critical components is the interconnect. Just like in inorganic tandems, that's a problem for us, at least in fully understanding it. And there's a number of ways to get around that. One of the ways is to use metallic nanoparticles as recombination sites in the interconnect layer. Or we could use a combination of some oxide materials and conducting polymers to act as efficient recombination layers. There's been even more results out of the small molecule group, the group at Dresden, where they're using combinations of fullerenes and in this case oligothiophenes, and they've gotten over 6% device in a recent publication on a junction device, multi-junction device. One very exciting announcement. So Yang group has certified well over 8% in a solution process tandem. So no vacuum deposition except for the electrodes. So a tandem device well over 8% has been demonstrated. So I refer you to Yang for a little more details on that. Okay, I want to touch briefly on degradation mechanisms. Yep. Okay. So there's really a lot of degradation mechanisms that we can consider in an OPV device. So ingress of water and oxygen that could further induce photooxidation or other chemical processes, delamination of the layers, migration of electrode materials into the device, so lots of different processes. But my message to you is that these are all engineering problems. These are not intrinsic limitations. And I'll give you some recent data from a variety of collaborators that really is very compelling. So the NREL group of Matt Lloyd, Dana Olson, and David Ginley has been making inverted devices. That's with the silver top contact, which you can actually measure unencapsulated, that have lifetimes that are stable out to 5,000 hours, and in fact, now approaching 5 years of lifetime completely stable. We can also do that with encapsulated devices, where you take the same device, encapsulate it between glass, so a very expensive encapsulation scheme. And the device is actually completely stable. In fact, is increasing in behavior past 1 year. And the extrapolated lifetime for this is now greater than 10,000 hours, and is still apparently going up at the 1 year point. So the point is that good encapsulation removes a lot of the oxidation processes, and the intrinsic polymer can be very stable. The Stanford group is now demonstrating extrapolated lifetimes beyond 7 years. This is a non-inverted device. And I refer you to Craig Peters' talk, which I believe is later this week on that topic. And then finally, the Heliotech group, actually they're extrapolating enormous lifetimes for these devices, something greater than 30 years from a small molecule device. So we have reason to believe that if you remove all solvent from the device, if it's thermally deposited, that you get really robust devices. Okay, finally the last portion of the talk on the economic potential, and I just have a few slides on this. So there's been a lot of work recently on modeling of the economics of OPV. There's been a number of groups doing this. One of the groups was a collaborator of Ryan Raffelli, the recent director of the National Center for Photovoltaics. So this was a life cycle assessment of organic solar cells and was a plot of energy payback time for a whole myriad of technologies. So these are all organic structures like P3HT, PCBM, or PTB7, C70. And this simple analysis finds that actually the energy payback time can be very competitive with existing thin film technologies. Now, as Howard pointed out, these economic analyses should be taken with a grain of salt. It's a very early area, and so I wouldn't rely strictly on one analysis, but at any rate, this looks pretty promising. And then the NREL strategic analysis group has been working very hard and to separate out all the costs of the module in terms of inks and electrode cost. And what they're finding is that the active layer materials are about $10 per meter squared. That would be at large-scale production, not at present-day cost. And so a total packaging cost of something like $15 per meter squared for a single-junction device and about $25 per meter squared for a multi-junction device. So if one projects forward a couple years to the point where the barrier materials have come down in cost, and this is projections now for the year 2014, and this includes both the active layer materials and all of the front and back cladding layers, one can think about cost below $1 per watt for the materials of the device. So there are no production costs in this quite yet. So for single junction, we think about 60 cents per watt, double junction, something like 50 cents, and then even lower for triple junction if we go that far. So some promising economic potential for the OPV. Okay, just a few closing remarks to wrap up. I want to point out that industrial upscaling has been nothing but good for organic PV. We've seen higher efficiencies and also better reproducibility. So by putting in better infrastructure and better capital equipment, we get much better reproducibility in the fabrication. And by the way, the prospects are for very high-speed printing and deposition. We're talking about something like meters per second rates out of some of these techniques. So device lifetime is an engineering problem, and it's really many fields of engineering: chemical, electrical, mechanical engineering. It's not an intrinsic problem of the die. One thing I want to point out again is material acquisition is a problem in the field. We have all these different potential materials, but for a university group or a small startup company to get good quality material is a problem. And this is something I would like to propose for the funding agencies and the national laboratories, is perhaps they can help catalyze a solution by inspiring new synthesis either by companies or federal laboratories that are provided to the community at a reduced cost. And finally, I showed one pathway to sort of a new efficiency regime for OPV. As I mentioned, we can think about others. And the point is that OPV is not simply a specific type of device, but it's really a platform for many different new mechanisms for photophysics and for carrier generation that we can think about. So that gives you an idea for some of the promising aspects for OPV. And with that, I'd like to conclude, and thank you for your attention.